Good evening, everyone. My name is Aishwarya Selvaraj. I am a second year PhD student at the ICRA node of Curtin. And today I'll be presenting some of the results from my ongoing research, which is titled as Improve Foreground Mitigation with the Central Redundant Array Megatile. To begin with, the figure on the right here shows the cosmic history of the early universe, which began with the Big Bang. After the Big Bang, the universe was hot and ionized. But as the universe began to expand, the ionized electrons and neutrons combined together to form neutral hydrogen. This resulted in the universe in going into the dark ages until a redshift of roughly around 30, when the first stars and galaxies began to form. As a result of the star formation, the radiation that's coming out from these sources began to ionize the region around it. And as the star formation continued, slowly, the universe completely transformed itself from being neutral to ionized. This period in the early universe, when the universe transformed from being neutral to ionized, is called as the epoch of reionization. Why is this period important? This is the period when the first stars and galaxies formed. Therefore, if we could understand this period in detail, we could begin to understand how the first stars and galaxies formed, what is the process of galaxy evolution, and what is the nature of those first stars. How do we probe this period? In general, there are many different ways to probe this period, but in today's talk, I'll be discussing about the 21 centimeter signal, which is caused because of the hyperfine splitting of the ground state atomic hydrogen because of the interaction between the magnetic moments of its electron and proton, that results in an energy difference that corresponds to a frequency of 1420 megahertz or 21 centimeter signal. The figure on the right here shows the time evolution of the 21 centimeter signal, that during the dark ages, the spin temperature of the 21 centimeter was decoupled from the CMB temperature, and as a result, it could be seen in the absorption spectrum. But as the reionization process began and the UV radiation started to come out from these sources, the 21 centimeter could be seen in the deep absorption spectrum. Now, with the reionization process, with the star formation that began, with the X-ray radiation that's coming out from these sources, the 21 centimeter could then be seen in the emission spectrum. So the bottom panel over here shows the global 21 centimeter signal, and the top panel over here shows the spatial fluctuations in the 21 centimeter signal. But because the universe is expanding, the 21 centimeter signal is redshifted to lower frequencies. Therefore, we require radio instruments to probe the signal. Currently, there are two types of experiments that is aiming to detect the signal. The first type of experiment consists of the global 21 centimeter experiment, such as the EDGES, which is aiming to detect the global average of the 21 centimeters of over the whole sky. While the second set of experiment is the interferometry-based experiment, such as the LOFA, HERA, and MWA. In the spirit of my research, today I'll be discussing details that's only pertaining to MWA. MWA, or Murchison Wildfield Array, is a low-frequency radio telescope that is located in the Radio Astronomy Observatory in the Murchison region of Western Australia. It operates in a frequency range of 80 to 300 megahertz. The phase 1 of MWA consists of 128 tiles, and the phase 2 consists of 256 tiles, where each of the tile consists of 4x4 dipole, where each of this dipole is spaced at a distance of 1.1 meters from each other. Even though MWA is located at a pristine radio quiet region in the world, a detection has so far yet not been made. The reason being, the signal is exceptionally weak. Therefore, calibration is necessary to remove the errors that's caused by the instrument and the sky to make a successful detection. What makes this challenging is the presence of foregrounds, such as the galactic and extragalactic sources that are of the order of magnitude 4 or 5 greater than the cosmological signal. Effectively, detecting the signal is like detecting the flapping of a hummingbird's wing amidst a hurricane. In addition, there's also the presence of the ionospheric distortions because we are observing in the low frequency regime. These challenges are being further compounded by the large field of view of the MWA telescope that sees a large portion of the sky. So the figure over here shows how the MWA telescope would see the patch of the sky in the EOR2 field. As you can see here, within the primary lobe of MWA, there are multiple foregrounds which contaminate the data set. In addition, there's also the presence of the galactic plane, which is passing through the side lobe, which is also contaminating the data set. At Curtin, the MWA-EUR group focuses on many different problems that is pertaining to the detection of the 21 centimeter signal. My project is a part of the jigsaw puzzle, which is aiming to detect the 21 centimeter signal, but using a new tool. Therefore, in my research, I work with this instrument called as the CRAM, or the Central Redundant Array Megatile, which is an external and a larger MWA tile, which is consisting of 8 by 8 dipoles, which is spaced at a distance of 1.1 meters from each other. The beamformer of CRAM is having equal delay, and therefore it's always pointing towards the zenith. The prime implication of having of using CRAM is that by increasing the size of the tile, we could reduce the field of view so that we can reduce the impact of the foregrounds on the EUR dataset. With that being said, where is CRAM installed? During the phase 2 upgradation of MWA, 72 new tiles were introduced to the existing core, which was arranged in an hexagonal compact array configuration. Because there's a spatial hole at the center of these hexagonal compact array configuration, currently, CRAM is installed at the center of the southern hexagonal compact array configuration, where there's a possibility of having redundant baselines, which could be used for foreground mitigation and redundant calibration in the future. With that, how do we expect to improve the EUR sign? In the statistical detection of the 21 centimeter signal using fast spectrum, we consider an EUR window, which is free of the foregrounds, where the foregrounds are confined within the region called as the wedge. So when we are trying to make the observation, we are confined within the EUR window, even though the signal has stronger signal to noise ratio within the K mode that is present within the wedge. So if by any means we could get those extra K modes, which is present in this wedge, we could improve the probability of a successful detection. How could we do this? Because the edge of the wedge is defined by the field of view of the instrument, by increasing the size of the tile, such as the CRAM, we could reduce the field of view and thereby reduce the impact and thereby reduce the size of the wedge and increase the parameter space of the EUR window. Additionally, because there are the foregrounds that is present in the foreground in the side lobes also leak into the EUR window, contaminate the data sets. By using a larger tile, we would reduce the number of side lobes and thereby reduce the impact of bright sources near the horizon. With that, it's important for me to understand the instrument in detail, for which I make frequent visit to the MRO to do maintenance activities. So this is from one of the trips that I had made last year to do maintenance activities on the instrument. Now, further, I have done simulations to understand and characterize the performance of CRAM. So this is the primary beam response of the CRAM, which is measured at 150 megahertz and compared with that of the MWA primary response. The figure on the left here shows the primary beam response of the MWA tile, and the figure on the right shows the primary beam response of the CRAM. As you can see here, with the larger tile, the field of view of CRAM is much smaller. In specific, the solid angle reduces by a factor of 4. In interferometry, we are interested in the cross-tile correlation between two tiles, where generally we would consider an MWA and an MWA tile to produce the power response. But instead, in my research, I'll be interested in producing the cross-tile correlation between an MWA and a CRAM to produce the power response, and the one-dimensional cross-section of this is as shown in the figure. As you can see here, the MWA CRAM baselines can have a much reduced response when compared to the MWA baselines. And also with the MWA CRAM, there are even negative response that has been obtained. This is quite important because it implies that with the MWA CRAM baselines, we can see the sky much differently when compared to that of the MWA baseline. To test this further, I consider a 1 Jansky point source and track the source as it goes from the horizon to the zenith and plot the flux density against the elevation angle. So the figure here shows that with the MWA CRAM baselines, it has a reduced response when compared to the MWA. In addition, the nulls of both the instruments align together because the number of dipoles is an integral multiple of each other. And in addition, even if within the side lobe of MWA, there are nulls which is present because of the MWA CRAM baselines. So effectively, if there was a source at those locations on the sky, even if MWA is showing a response with the CRAM baselines, we could have a much reduced response and thereby reduce the impact on the EUR dataset. Now, I'm working in on it further to test it by computing the power spectrum and trying to understand how much of an improvement can be obtained by using MWA and CRAM baseline. So this is an ongoing work which needs further investigation. And with that, I would like to end my talk. Thank you.